What if the very foundations of your reality, everything you accept as true about the cosmos, were built on a misconception? Just look up at that sea of stars on a clear night, that breathtaking expanse that feels so eternal and so vast. It's a view that has inspired humanity for millennia, a canvas for our stories and our science. But what if I told you that our most fundamental ideas about space, time, and our own existence are being rewritten right now by discoveries so bizarre they sound more like science fiction? We are living through a golden age of cosmic revelation, where every new telescope and every new calculation peels back another layer of the grandest mystery of all. This isn't just about learning new facts, it's about having our entire perspective on the universe fundamentally shifted. We are on the verge of understanding realities that were, until very recently, completely hidden from us, truths that challenge the very nature of what is possible. It's a thrilling and perhaps slightly unsettling place to be, and that sense of awe and wonder is exactly what we're going to lean into today. This journey isn't about dry equations or distant abstract theories. It's a tour of the cosmos's greatest hits, the most shocking, the most beautiful, and the most head-scratching truths that modern astrophysics has to offer. We're going to explore realities where time slows to a crawl, where invisible forces dictate the fate of galaxies, and where the vacuum of space itself seethes with unimaginable energy. These aren't just curiosities for scientists in lab coats. They are clues to the ultimate puzzle of where we came from and what our universe is truly made of. Each one of these truths is a piece of a much larger story, a narrative that is still being written, and you have a front row seat. So get ready to have your mind stretched in ways you didn't think were possible. We are about to dive deep into 30 surprising truths about the universe, a collection of ideas that will challenge what you thought you knew, spark your imagination, and leave you looking at the night sky with a completely new sense of wonder. This is going to be fun. Let's begin with a truth so profound it redefines our place in the cosmos. The universe you see is only a tiny fraction of what's actually there. Every star, every galaxy, every planet you can observe through a telescope, all of that normal, tangible stuff, the matter that makes up you and me and everything we've ever known, accounts for less than 5% of the entire universe. The other 95% is made of things we cannot see, forces we are only beginning to comprehend. We call these mysterious components dark matter and dark energy. Think of it like an iceberg. The part of the iceberg you see floating above the water is stunning and impressive, but it's just a small piece of the whole structure. The real mass, the immense bulk of the iceberg, is hidden beneath the surface, invisible, yet it's what truly dictates how the iceberg moves and behaves. Our universe is exactly like that. The glittering galaxies are just the visible tip, while the vast, unseen depths are ruled by these dark components. Dark matter is the cosmic scaffolding. We can't see it or touch it because it doesn't emit, absorb, or reflect any light, hence the name dark. But we know it's there because of its immense gravitational pull. We see its ghostly hand at work in the way galaxies spin. The stars at the outer edges of spiral galaxies are whirling around so fast that, according to the gravity from the visible matter alone, they should be flung off into the void. The fact that they aren't tells us there must be a huge amount of invisible matter surrounding each galaxy, creating a gravitational grip strong enough to hold everything together. Without this dark matter halo, galaxies like our own Milky Way would have never formed and would simply fly apart. Then there's dark energy, which is even more baffling. While dark matter acts as a cosmic glue, pulling things together, dark energy is doing the exact opposite. It's pushing the universe apart at an ever-increasing rate. Imagine blowing up a balloon with tiny dots on it. As you inflate it, the dots all move away from each other. Now imagine that instead of you blowing, the balloon starts inflating all on its own, and it starts inflating faster and faster over time. That's the effect of dark energy. It's a repulsive force woven into the very fabric of space itself, and it's causing the expansion of our entire cosmos to accelerate. So here we are, living in a universe where the stuff we're made of is the rare exception, not the rule. The grand cosmic dance is being choreographed by invisible partners, with dark matter sculpting the large-scale structure of the cosmos and dark energy writing its ultimate fate. It's a humbling reminder that what we perceive as reality is just a sliver of a much deeper and far more mysterious whole. And that unsettling idea that nearly everything in the cosmos is invisible to us leads us directly to our next astonishing truth, one that challenges our most basic understanding of what nothing really means. If you were to take a perfect box and remove every single atom of gas, every speck of dust, every photon of light, you would be left with what science calls a perfect vacuum. Classically, we would call this empty space. But the universe has a surprise for us. That so-called emptiness is not empty at all. In reality, it is a seething, frenetic, and wildly active arena, boiling with energy and teeming with fleeting particles that defy our everyday logic. This bizarre and bustling activity at the smallest possible scales is known as quantum foam, and it reveals that the very fabric of space-time is anything but smooth and tranquil. Think of the calmest, most placid ocean surface you can picture. From a distance, it looks like a sheet of glass, but if you could shrink down to the size of a plankton and look closely, you would see a tumultuous, churning world of waves, bubbles, and ceaseless motion. The quantum vacuum is like that. At scales 1 billion times smaller than an atom, the smooth stage of space and time breaks down into a frothing, turbulent foam. In this realm, the rules of classical physics we know and love are suspended, and the far stranger laws of quantum mechanics take over. Here, the principle of quantum uncertainty allows for a remarkable phenomenon. Pairs of virtual particles, a particle and its antimatter counterpart, can spontaneously pop into existence, borrowing energy from the vacuum itself for an immeasurably brief moment before they collide and annihilate each other, paying back the energy loan. This isn't just a theoretical idea, we have experimental proof. The Casimir effect, for instance, demonstrates this beautifully. If you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, they will be gently pushed toward each other. Why? Because the tiny gap between the plates is so small that only certain wavelengths of virtual particles can flicker into existence there. Outside the plates, a much wider sea of virtual particles can form, creating a kind of pressure that forces the plates together. It's a measurable force born from the activity of nothingness. This ceaseless creation and destruction isn't just a curious sideshow, it has profound consequences. The energy contained in this vacuum flux, known as zero-point energy, is believed to be unimaginably vast. In fact, some calculations suggest that the energy in a single cubic centimeter of empty space could be greater than the energy in all the visible matter in the entire universe. This staggering energy might even play a role in the behavior of dark energy, driving the accelerated expansion of the cosmos. So the next time you gaze up at the vast, dark void between the stars, remember, you are not looking at a sterile, passive emptiness. You are witnessing a foundational layer of reality, a quantum ocean in a state of perpetual ferment. The universe has no true vacuum, no absolute nothingness. Every single point in space, from the void between galaxies to the air in front of your face, is a humming, vibrant field of potential, a constant reminder that at its most fundamental level, reality is built on a foundation of relentless dynamic activity. If the very fabric of space is a restless quantum sea, then what does that mean for time itself? This brings us to one of the most mind-bending truths of all. Time is not a universal, constant river flowing at the same rate for everyone. It is a deeply personal and flexible experience, a river that flows at different speeds depending on where you are and how you're moving. This isn't science fiction. It's a fundamental prediction of Einstein's theory of relativity, and it has been confirmed by experiments time and again. Einstein shattered the classical notion of a single, objective clock for the universe. He revealed that space and time are woven together into a single fabric called space-time, and that this fabric can be warped and stretched by two things, gravity and velocity. The stronger the gravity you experience, the slower your time flows relative to someone in a weaker gravitational field. This is called gravitational time dilation. Imagine two identical, highly precise clocks. You place one on the surface of the Earth, and you launch the other into orbit on a satellite. When you later compare them, you'll find the clock on the satellite has actually ticked faster than the one on the ground. This happens because the satellite, being farther from Earth's mass, experiences slightly less gravity, allowing its time to run a tiny bit quicker. The same principle applies on a more dramatic scale. If you could stand on the surface of a neutron star, an object with immense gravity, your time would slow to a crawl compared to someone watching you from a safe distance. They might see you take 1,000 years just to lift your hand, while for you, it would feel like a normal movement. The other way to slow time is to move, and I mean really move. According to special relativity, as your speed through space increases, your speed through time decreases. The closer you get to the speed of light, the more your personal clock slows down relative to someone who is stationary. This is known as velocity time dilation. Picture a pair of twins. One stays on Earth while the other embarks on a journey through space in a rocket traveling at 90% the speed of light. When the traveling twin returns after what felt like a few years to them, they would step out of the ship to find their Earth-bound sibling has aged decades. The astronauts' high-speed travel literally slowed their rate of aging. Now, you might be thinking this all sounds like an obscure effect that only matters for astronauts and theoretical physicists. But the truth is, you rely on this bizarre reality every single day. The Global Positioning System, or GPS, is a perfect, everyday proof that time dilation is real. The network of GPS satellites orbiting our planet are moving at high speeds and are located in a region of weaker gravity compared to the surface. Both of these factors affect their onboard atomic clocks. Compared to clocks on the ground, the satellite's clocks run faster by about 38 microseconds each day. That might not sound like much, but if the system's computers didn't constantly correct for this relativistic effect, the GPS coordinates your phone gives you would drift by over 6 miles each day, rendering the entire navigation system useless within minutes. So, every time you use your phone to find a coffee shop or get driving directions, you are personally harnessing the strange, mutable nature of time as described by Einstein. This proves that time is not a backdrop against which the universe plays out. It is an active, dynamic participant, different for every observer. Your past, present, and future are not absolutes. They are intimately tied to your own journey through the warped and woven canvas of space-time. Now, if time itself is a personal experience shaped by gravity and motion, then what about our location in the cosmos? This leads us to a truth that completely overturns a very intuitive yet deeply incorrect idea we all carry, the notion that the universe has a center. We often picture the Big Bang as a titanic explosion, a cosmic bomb that went off at a single location, hurling galaxies outward into a pre-existing empty void. It's a powerful and natural mental image, but it is fundamentally wrong. The reality is far more strange and profound. The Big Bang did not happen somewhere in space, it happened everywhere at once. It was the simultaneous and rapid expansion of all of space itself from a state of incredible density and heat. This means there is no central point to the universe, no place you can point to and say, it all started right there. Instead, every single point in the cosmos was, in a very real sense, the center of that initial event. A wonderful analogy to help visualize this is to think of the universe as a loaf of raisin bread dough before it is baked. Imagine that the dough represents the fabric of space itself, and the raisins scattered throughout represent galaxies. As the dough proofs and rises, it expands uniformly. From the perspective of any single raisin, all the other raisins are moving away from it. A raisin near the edge doesn't see all the others rushing toward one side of the oven. It sees the entire loaf expanding around it, making every raisin feel as though it's at the center of the expansion. This is precisely what we observe in our own universe. No matter which galaxy an astronomer calls home, they will measure all the other galaxies as receding from them. We are not being pushed away from a special central location. The very space between all galaxies is stretching, creating the appearance of a universal recession from every possible vantage point. This discovery shatters any lingering idea that we occupy a privileged or central position in the cosmos. The principle, known as the cosmological principle, tells us that the universe is both homogeneous and isotropic on the largest scales. In simpler terms, it means the cosmos looks roughly the same in every direction and from every location, with no grand center and no discernible edge. There is no outside to the universe, just as there is no outside to the surface of a balloon as it inflates. This realization is both humbling and liberating. It means we are not exiled to some cosmic backwater, nor are we sitting at the heart of creation. We are simply part of the grand, unfolding fabric, a participant in a cosmic process that is happening uniformly everywhere. Every spot in the universe, from the most distant quasar to the planet you're standing on right now, can claim to be at the center of its own observable horizon, with the rest of the cosmos stretching away in all directions. This truth forces us to abandon a deeply ingrained, Earth-centered perspective and embrace a truly universal point of view, one where the concept of a center loses all meaning in the vast, expanding whole. Now, following that idea that we are all part of a vast, centerless expansion, let's turn our gaze inward to one of the most beautiful and intimate truths of all. You are not just a passive observer of this cosmic drama. You are a literal piece of it, forged in the most violent and creative events the universe has to offer. Every single one of us is made of stardust. This is not a poetic metaphor, but a scientific fact. Nearly every atom that constructs your body, the calcium in your bones, the iron in your blood, the oxygen you breathe, was created in the nuclear furnace of a star that lived and died long before our sun was even a glimmer in the cosmos. Let's trace this incredible journey. In the very beginning, after the Big Bang, the universe was a much simpler place. For several minutes, it was hot and dense enough to fuse the primordial hydrogen and helium into tiny traces of lithium, but that was it. The cosmic kitchen shut down, leaving a universe filled with about 75% hydrogen and 25% helium. There were no carbon atoms, no nitrogen, no oxygen, none of the complex ingredients necessary for planets, oceans, or life. For the next several 100 million years, these simple gases pooled together under gravity, eventually igniting into the first generation of stars. And inside these stellar forges, the magic began. Through the process of nuclear fusion, the intense pressure and heat at a star's core smashed lighter atoms together to create heavier ones. A star like our Sun spends its life fusing hydrogen into helium, which is a remarkable process in itself. But more massive stars, true cosmic powerhouses, can go much further. In their layered, onion-like interiors, they fuse helium into carbon, carbon into oxygen, and on, creating neon, magnesium, and silicon, all the way up to iron. But here's the catch: the creation of elements stops at iron. Fusing iron doesn't release energy, it consumes it. It's the stellar equivalent of a dead end. So how did the copper in your electrical wiring, the gold in a wedding ring, or the iodine in your thyroid get here? The answer lies in the spectacular death of these massive stars, the supernova. When a giant star exhausts its nuclear fuel, its core collapses catastrophically in a matter of seconds. This collapse triggers a titanic rebound explosion, a supernova that for a brief moment outshines an entire galaxy. In this unimaginable inferno of energy and neutrons, a frantic blizzard of nuclear reactions occurs, forging all the elements heavier than iron. In a similar, equally violent process, the collision of two ultra-dense neutron stars can also seed the cosmos with these precious heavy elements. The supernova explosion then acts as a cosmic farmer, scattering this newly forged stardust, a rich mixture of carbon, oxygen, nitrogen, iron, gold, and uranium across interstellar space. This debris, mixed with the primordial hydrogen and helium, eventually coalesces into new clouds of gas and dust. It was from such an enriched cloud, seeded by the deaths of countless ancient stars, that our own solar system formed 4.5 billion years ago. So, when you look at your own hand, you are looking at a collection of atoms that have been on an epic voyage across space and time. The oxygen you just inhaled was likely forged in two different stars, some from a long-gone giant star and some from the Sun. The iron carrying oxygen in your blood was definitely synthesized in the final moments of a massive star's life, just before it went supernova. This means that we are not just biologically connected to other life on Earth, we are atomically connected to the entire cosmos. The same carbon that forms the backbone of your DNA is the same carbon that makes up the rings of Saturn and the atmosphere of distant exoplanets. We are the universe become conscious, a way for the cosmos to look back on itself and understand its own incredible history of creation and destruction. And that profound connection, the very atoms of our being tracing back to stellar cataclysms, forces a question of almost unimaginable scope. What if the laws of physics that allowed those stars to form, burn, and explode in just the right way to create us aren't universal and eternal truths? What if they are merely the local bylaws of our own cosmic neighborhood? This brings us to one of the most controversial and mind-expanding ideas in all of science: the possibility that our universe is just one of countless others in a vast multiverse, each with its own unique and perhaps wildly different set of physical rules. The constants we take for granted, the strength of gravity, the mass of an electron, the force that holds atomic nuclei together, feel so fundamental and precise. They seem to be perfectly tuned or fine-tuned for the emergence of complex chemistry and ultimately life. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself immediately after the Big Bang. If it were slightly weaker, matter would never have clumped together to form stars and galaxies. If the nuclear strong force were a fraction of a percent different carbon atoms, the essential building block of life as we know it would never have been stable inside stars. It's as if someone set dozens of dials with exquisite precision to create a universe capable of hosting us. This apparent fine-tuning has led some to propose a designer, a cosmic architect. But another, purely naturalistic explanation has gained traction in theoretical physics: the multiverse. The idea is that what we call the universe is just one expanding bubble in an infinite, frothing sea of space-time foam. In this eternal inflation, new universe bubbles are constantly budding off, each with its own random set of physical constants and laws. In this vast cosmic lottery, most of these universes would be stillborn or barren. A universe where gravity is too strong might instantly become a black hole. One where the electromagnetic force is too weak might never form atoms. We quite obviously find ourselves in one of the rare, lucky universes where the dials were set just right for stars, planets, and life to emerge. We shouldn't be surprised to find ourselves in a habitable universe. We couldn't exist in any of the uninhabitable ones. This isn't a testable hypothesis in the traditional sense. We can't peer into other universes, but it emerges naturally from our best theories of cosmic inflation and quantum mechanics. Think of it like this: if you were a fish that could only live in fresh water, you might assume all water is fresh. It would be a shock to learn about the vast, salty oceans that cover most of the planet, environments where you couldn't survive for a moment. Our universe, with its specific, life-friendly laws, might be like a single freshwater pond in a cosmic landscape full of saltwater seas, acidic lakes, and lakes of liquid methane. Our local laws of physics aren't special or chosen. They are simply the ones we ended up with, and they allowed us to be here to ponder the question. This concept completely upends our perspective. The laws of physics are no longer seen as necessary and preordained truths, but as potentially accidental and variable. It suggests a reality of literally incomprehensible scale and diversity, where the very logic of existence changes from one bubble to the next. While it may seem like a wild, untestable idea, it provides a powerful and elegant answer to the puzzle of fine-tuning, forcing us to confront the humbling possibility that our entire reality is just one page in an infinite library of realities, most of which would be utterly alien and unrecognizable to us. Yet, even the most extreme and seemingly permanent objects in the cosmos are not immune to the strange rules that govern the quantum sea. This leads us to a truth that redefines the ultimate fate of the universe's most terrifying phenomena: black holes are not eternal. For decades, we pictured them as the ultimate cosmic vacuums, absorbing everything that crosses their event horizon, growing ever larger and more powerful, and holding onto their captured mass and energy forever. But thanks to the brilliant work of Stephen Hawking, we now understand that black holes can, in fact, evaporate, slowly leaking their substance back into the universe over trillions upon trillions of years. The key to this incredible process lies right at the boundary of the black hole, the point of no return known as the event horizon. Remember that restless quantum foam we discussed, the seething vacuum where particle-antiparticle pairs constantly flicker in and out of existence. Normally, these virtual pairs annihilate each other almost instantly, but something truly bizarre happens when this quantum fluctuation occurs right at the edge of a black hole. Imagine one of these virtual pairs popping into being just at the precipice. In a fantastically rare but statistically inevitable event, one particle of the pair falls across the event horizon while its partner manages to escape. From the perspective of an outside observer, the black hole has just emitted a particle. This is Hawking radiation, but there's a cosmic price to be paid for this emission. The particle that fell into the black hole has negative energy relative to the outside universe. To balance the cosmic books, the black hole itself loses a tiny, tiny amount of mass. It's as if the black hole has paid for the creation of the escaped particle with a sliver of its own being. This isn't a fast process. For a typical black hole with the mass of our Sun, the amount of Hawking radiation it emits is so incredibly faint that it is completely drowned out by the cosmic microwave background radiation, the leftover heat from the Big Bang. The temperature of a black hole's Hawking radiation is inversely related to its mass. The more massive the black hole, the colder it is, and the slower it evaporates. A stellar mass black hole has a temperature of just a fraction of a degree above absolute zero, and its evaporation process would take longer than the current age of the universe. But as the universe expands and cools over unimaginable eons, the background temperature will eventually drop below that of even the largest black holes, and this slow leak will begin in earnest. The evaporation process is a slow drip at first, but it accelerates as the black hole loses mass. As it gets smaller, its temperature rises, causing it to radiate energy away even faster. In the final, spectacular moments of its life, a black hole that has been evaporating for trillions of years would shrink rapidly, its temperature soaring to incredible levels until it vanishes in a final, violent burst of high-energy gamma rays. This profound discovery connects the three great pillars of modern physics: gravity, quantum mechanics, and thermodynamics. Hawking showed that black holes have entropy, a measure of disorder, and a temperature, meaning they behave like thermal objects. This resolved a major paradox about what happens to information that falls into a black hole, a puzzle that physicists are still refining the answer to today. So the image of the black hole as a perfect, eternal prison is shattered. It is instead a dynamic, evolving object, slowly returning its energy to the cosmos, a testament to the fact that even in the most absolute darkness, the restless churn of the quantum vacuum ensures that nothing lasts forever. If the evaporation of a black hole shows us that even the most absolute objects are subject to quantum weirdness, then prepare for a concept that challenges the very sequence of reality as we experience it. We are now going to explore a truth so counterintuitive that it seems to defy logic itself: the unsettling possibility that the future can reach back and influence the past. This isn't about psychics or prophecy. It's a serious interpretation emerging from the deepest puzzles of quantum mechanics, known as retrocausality. Our entire lives are built on the unshakable belief that cause must always precede effect. A rock breaks a window after it is thrown. You feel pain after you stub your toe. This forward march of time, this arrow of causality, is the bedrock of our reality, but in the quantum realm, this arrow might be able to point both ways. The classic experiment that highlights this bizarre possibility is the famous double-slit experiment. When you fire a stream of particles like electrons at a barrier with two narrow slits, they don't just form two clusters on the detector screen behind it. Instead, they create an interference pattern, a series of light and dark bands, as if each individual electron is behaving like a wave, passing through both slits at once and interfering with itself. This is strange enough, but it gets weirder. If you place a detector at the slits to figure out which path each electron actually takes, the interference pattern vanishes. The mere act of measuring, of observing the particle's path, forces it to behave like a single, well-defined particle, and the wave-like interference is destroyed. It's as if the electron knows it's being watched. Now, take this one step further into the truly mind-bending territory with a variation called the delayed choice quantum eraser. In this experiment, scientists can set up the equipment so that the choice of whether to measure the particle's path or to erase that information is made after the particle has already passed through the slits and is on its way to the final screen. According to our everyday logic, the particle should have already decided whether it was a particle taking one path or a wave taking both paths by the time it passes the slits. But that's not what happens. The results show that the choice the experimenter makes in the future after the particle's journey has begun determines the behavior of the particle in the past. If the future choice is to erase the which path information, an interference pattern emerges on the final screen, meaning the particle acted as a wave back at the slits. If the future choice is to measure the path, then no pattern appears, meaning the particle acted as a single particle back at the slits. It's as though the particle's history is not fixed until the moment it is ultimately observed. How can we possibly make sense of this? One interpretation is that causality is not a one-way street. The future measurement event is, in a very real sense, reaching backwards in time and influencing the state of the particle at the earlier moment. Another way to think about it is to let go of the idea that particles have definite properties at all until they are measured. In this view, the particle exists in a fuzzy cloud of all possible states, a superposition, and it's only the final act of detection that solidifies its entire history from start to finish. Imagine mailing a letter without an address, and the act of someone opening it at the destination office determines which city it was originally sent from. It sounds impossible, yet this is the kind of logical acrobatics the quantum world demands. This doesn't mean you can go back and change your own personal history in a macroscopic way. These effects are isolated to the quantum level and are incredibly difficult to sustain or observe at larger scales. But the philosophical implications are staggering. It suggests that the flow of time as we perceive it, a relentless, linear progression from past to future, may be an illusion, an emergent property of our macroscopic world that simply doesn't apply at the fundamental level of reality. The universe at its heart may not distinguish between past and future with the clarity we assume. Trying to make sense of that quantum strangeness where the future seems to whisper to the past can feel like trying to grasp smoke. But what if the ultimate source of that confusion isn't in the tiny quantum world, but in our own perception? This brings us to a truth that is perhaps the most speculative on our list, yet one that emerges directly from the elegant mathematics of our most fundamental physical laws. There is a compelling theoretical possibility that our universe has a perfect mirror image, a cosmic doppelganger where time runs backwards, antimatter is the norm and left is right. This is the concept of the CPT symmetric universe. To understand this, we need to look at the fundamental symmetries that physicists believe underpin all of reality. We have three core symmetries that our laws of physics seem to respect. The first is charge or C symmetry. If you take a particle and swap its electrical charge, replacing it with its antimatter counterpart, an electron with a positron, for instance, the laws of physics should work the same way. The second is parity or P symmetry. This is the idea that the laws of physics are the same if you look at their mirror image. If you swap left for right, the universe should operate identically. The third is time or T symmetry. This suggests that if you could run time backwards, the fundamental processes should still obey the same physical rules. For a long time, physicists believed that each of these symmetries was inviolable on its own. But then came a series of shocking discoveries. In the 1950s, it was found that the weak nuclear force, which is responsible for certain types of radioactive decay, actually violates parity. In simple terms, many subatomic processes have an inherent handedness. They prefer one direction over its mirror image. It's as if the universe has a tiny but fundamental preference for left-handedness in certain interactions. Then it was discovered that this same force also violates CP symmetry. That is, if you simultaneously swap a particle for its antiparticle C and look at its mirror image P, the resulting process is still slightly different from the original. This was a monumental finding because it pointed to a fundamental arrow in time, a built-in distinction between past and future at the microscopic level. So, if CP symmetry is violated, how does the universe maintain its overall balance? The answer appears to lie in the combination of all three. The CPT theorem is a cornerstone of modern quantum field theory, and it states that the universe must be perfectly symmetric under the combined transformation of all three operations at once, swapping particles with antiparticles C, creating their mirror image P, and reversing the direction of time T. If our universe violates CP symmetry, then to preserve the overall CPT symmetry, it must also violate T symmetry. There must be a fundamental difference between forward and backward time at the most basic level. This is where the mirror universe idea emerges in its most compelling form. If you apply the full CPT transformation to our entire cosmos, the mathematics doesn't just describe a different set of particles, it describes a whole new universe. In this CPT mirror universe, everything would be flipped. All of our matter would be replaced with antimatter. The chirality or handedness of all molecules and physical processes would be reversed. What was left-handed here would be right-handed there. And most mind-bending of all, time would flow in the opposite direction. From our perspective, this universe would be evolving backwards in time. Now, what would such a universe look like from the inside? If we could somehow peer into it, would we see scrambled eggs leaping from the pan back onto the shell, or people walking backwards? Almost certainly not. Consciousness and perception are almost certainly emergent phenomena tied to the thermodynamic arrow of time, the increase of disorder or entropy. In that CPT universe, the thermodynamic arrow would also be reversed. Entropy would be decreasing from our point of view, but for any hypothetical observers inside that universe, their perception would be aligned with their local arrow of time. They would experience time flowing forward from their past to their future, which is our future to our past. They would remember what we would consider the future and anticipate what we call the past. To them, our universe would be the one where time runs backwards. This isn't just a fun thought experiment. It provides a potential, natural explanation for one of the universe's great mysteries, the matter-antimatter asymmetry. Our observable cosmos is overwhelmingly made of matter, with very little primordial antimatter. We don't know why. The CPT mirror universe theory offers an elegant solution. Perhaps the Big Bang created a perfectly symmetric pair of universes, one made mostly of matter with time flowing as we perceive it, and its CPT twin, made mostly of antimatter with time flowing in reverse. The two universes together would form a perfectly CPT symmetric whole, satisfying the fundamental laws while individually appearing wildly asymmetric. We can never contact or observe this mirror cosmos, as it would literally be evolving in the opposite temporal direction, but its potential existence reminds us that our reality might be just one half of a grander, more balanced duality. It suggests that the flow of time we hold so dear may not be a universal absolute, but merely a local condition, a single thread in a tapestry of reality far more vast and symmetrical than we can possibly imagine. Building directly on the idea of a mirror universe, we're forced to confront the ultimate fate of our own. And as we turn our attention to that future, we find one of the most significant and startling discoveries in all of modern cosmology, a truth that not only rewrote the final chapter of our universe, but revealed a force so alien it defies our very understanding of physics. The universe is not just expanding, that expansion is accelerating, getting faster and faster with every passing moment. For most of the 20th century, the prevailing scientific view was that the universe, having been born in the explosive fury of the Big Bang, was now coasting outward. The mutual gravitational pull of all the matter in the cosmos was expected to be acting like a cosmic brake, gradually slowing the expansion down. The big question for astronomers was whether there was enough matter to eventually halt the expansion and pull everything back together in a big crunch, or if the universe would just keep expanding forever, albeit at an ever-slowing pace. To settle this cosmic debate, two independent teams of researchers set out in the late 1990s to measure the expansion rate over cosmic time by studying distant supernovae. They used a specific type of stellar explosion, a Type 1 supernova, which acts as a standard candle. Because these supernovae have a known, consistent intrinsic brightness, astronomers can measure how bright they appear from Earth and precisely calculate their distance. Furthermore, by analyzing the redshift of their light, how much it has been stretched to longer, redder wavelengths by the expansion of the universe, they can determine how fast the universe was expanding when that star exploded billions of years ago. The results were not just surprising, they were paradigm-shattering. The data from these incredibly distant supernovae showed that they were significantly fainter and therefore farther away than they should have been if the universe had been expanding at a steady or slowing rate. The only possible explanation was that the expansion of the universe was not slowing down at all. Instead, it was speeding up. Some mysterious, repulsive force was overpowering the collective gravity of all the galaxies, clusters, and dark matter, pushing the fabric of space apart with increasing vigor. This was the moment we discovered dark energy in an observational, concrete way. It was a discovery that earned the team leaders the Nobel Prize in Physics in 2011 and fundamentally altered our cosmic worldview. The implications of this accelerating expansion are profound and, in the very long term, deeply isolating, because this acceleration is not a one-time event but an ongoing process. Its effects compound over time. Imagine each galaxy is a raisin in that rising loaf of bread dough, but now the yeast has gone into overdrive. The dough isn't just rising, it's expanding at an ever-increasing rate. The raisins that are already close to each other, bound by their local gravity like the galaxies in our own local group, will stay together. But the vast, empty tracts of space between these gravitationally bound islands are stretching at a rate that will eventually become unstoppable. In the distant future, galaxies outside our immediate neighborhood will begin to recede from us faster than the speed of light. Now, this doesn't violate Einstein's theory of relativity, because it is space itself that is expanding faster than light can travel across it. The galaxies themselves aren't moving through space at superluminal speeds. The space between us and them is simply growing so rapidly that their light can no longer bridge the gap. The consequence is a future universe that grows quieter, darker, and more lonely with each passing eon. Billions of years from now, any astronomers in our galaxy will look out into the void and see a very different cosmos. The countless galaxies we see today, scattered across the deep fields of the Hubble and James Webb Space Telescopes, will have vanished. One by one, their light will redshift into oblivion, and they will cross an event horizon, disappearing from our observable universe forever. The evidence of the larger cosmos will simply fade away, leaving our Milky Way and its nearby galactic companions adrift in an immense, black, and seemingly empty void. The cosmic microwave background radiation, the afterglow of the Big Bang, will have been stretched to such long wavelengths that it will become undetectable. The universe will have effectively erased its own history, leaving future civilizations with no clues that a vast, populated cosmos ever existed beyond their own galactic doorstep. This is the ultimate fate dictated by dark energy, a heat death not of fire and collapse, but of cold, silent, and eternal isolation. It paints a picture of a cosmos that is not only stranger than we imagine, but whose final act is one of profound and permanent separation. Moving from a universe that may have a mirror image to one where particles themselves share a ghostly connection, we encounter a phenomenon so strange that even Albert Einstein himself found it deeply troubling, famously dismissing it as spooky action at a distance. This is the bizarre and beautiful world of quantum entanglement, a cornerstone of quantum mechanics that challenges our most basic intuitions about space, distance, and reality itself. At its heart, entanglement is a profound connection that can form between two particles, like electrons or photons. Once they become entangled, they are no longer independent entities. Their fates are linked in an intimate dance, no matter how far apart they are moved. Imagine you have a pair of magical, interconnected coins. You don't know whether each coin is currently showing heads or tails. They exist in a fuzzy superposition of both possibilities. You take one coin and travel to the farthest galaxy, while your friend stays here with the other. The moment your friend looks at their coin and sees it land on heads, your coin, instantaneously and with no time delay, will be forced to show tails. The act of observing one particle here collapses the shared quantum state of both, determining the outcome for its distant partner. This instantaneous connection appears to violate a fundamental rule in Einstein's theory of relativity, that nothing, not even information, can travel faster than the speed of light. Einstein was deeply unsettled by this, believing it pointed to a flaw in quantum theory. He, along with colleagues Boris Podolsky and Nathan Rosen, proposed the EPR paradox as a thought experiment to show that if quantum mechanics was correct, it would allow for this spooky, faster-than-light influence, which he felt was impossible. He preferred the idea that particles must have hidden, predetermined properties from the moment they are created, like a pair of gloves where one is for the left hand and one for the right. You just don't know which is which until you look. For decades, this was a philosophical debate, but then physicist John Bell devised a mathematical way to test it. Bell's theorem showed that if hidden variables were real, there would be a limit to the correlations between the particles. If quantum mechanics was correct, the correlations would be stronger. In the decades since, experiment after exquisitely precise experiment has confirmed the quantum prediction. When we measure one entangled particle, its partner responds instantaneously, and the correlations between them are stronger than any hidden variable theory could allow. This spookiness is real, so how are they doing it? How can information seem to travel faster than light? The most widely accepted explanation is that there is no information being sent between them in the conventional sense. It's not a signal. Instead, think of the two entangled particles not as two separate objects, but as a single, unified quantum system. Even when they are on opposite sides of the galaxy, they are still part of one system. The act of measurement here doesn't send a message to the other particle. It simply defines a property of the entire, non-local system at once. It's like having a single piece of paper that you tear in half. On one half, you write the word yes, and on the other, no. You mail one half to a friend across the world without looking at it. The moment you open your envelope and see yes, you know instantly, without any communication, that your friend has no. The information wasn't transmitted, it was inherent in the system from the start. This concept of non-locality suggests that at a fundamental level, the universe may be far more interconnected than it appears. The empty space separating you from the stars might be an illusion with a deeper layer of reality where distance is meaningless. This isn't just a theoretical curiosity. It's the foundation for emerging technologies like quantum computing and quantum cryptography. In quantum encryption, for instance, any attempt to eavesdrop on a message sent using entangled photons would immediately disturb their fragile connection, alerting the users to the presence of an intruder. It's a form of security guaranteed by the laws of physics themselves. So, while Einstein may have been spooked, his skepticism ultimately led to experiments that proved the universe is in fact far stranger and more wonderfully interconnected than even he could have imagined. But even as we grapple with the vast, interconnected nature of the cosmos, one of the most fundamental relationships in our own celestial backyard is undergoing a slow, steady change. The moon, our constant companion in the night sky, is quietly and gradually leaving us. It's receding from Earth at a rate of roughly 3.8 centimeters each year, a distance about equal to the width of your thumb. This isn't a sudden or alarming departure, but a profound, ongoing process driven by the timeless dance of gravity and the ocean's tides. The mechanism behind this lunar retreat is a fascinating transfer of energy, all thanks to the tug of war between the moon's gravity and Earth's rotating oceans. The moon's gravitational pull doesn't just lift the oceans to create the tides. It also creates a slight bulge in the water on the side of Earth facing the moon. However, because Earth is spinning on its axis so rapidly, much faster than the moon is orbiting us, this tidal bulge is actually dragged a little bit ahead of the direct line between Earth and moon. Think of it like this: Earth is spinning eastward, and the moon's gravity is trying to pull the tidal bulge directly toward it. This causes the bulge to lead slightly ahead of the moon's position. This off-center bulge, in turn, exerts its own gravitational pull on the moon. That extra tug is just enough to give the moon a tiny boost in its orbit, like a parent giving a gentle push to a child on a swing, nudging it into a slightly higher and therefore slower orbit. But in the cosmos, you never get something for nothing. The energy that is being transferred to the moon to push it away has to come from somewhere, and it comes at a direct cost to Earth itself. The friction of the tidal bulge being dragged across the ocean floors and continents acts as a constant brake on our planet's rotation. This means Earth's spin is very, very gradually slowing down, making our days longer. This effect is minuscule on a human timescale. A day gets only about 1.7 milliseconds longer per century, but over geological ages it adds up in a dramatic way. 400 million years ago, during the age of the dinosaurs, a day on Earth was only about 22 hours long, and a year contained nearly 400 of these shorter days. We see evidence of this in the growth patterns of fossilized corals, which lay down daily and seasonal bands, providing a natural calendar of Earth's deep past. As this process continues into the distant future, the consequences will become even more significant. The most immediate and perhaps most poignant change will be the end of total solar eclipses as we know them. A total solar eclipse is a stunning cosmic coincidence. The Sun is about 400 times larger than the Moon, but it's also about 400 times farther away. This perfect alignment makes the Moon appear almost exactly the same size as the Sun in our sky, allowing it to block the Sun's brilliant face while revealing its ethereal outer atmosphere, the corona. But as the Moon drifts farther away, its apparent size in our sky will slowly shrink. In an estimated 600 million years, the Moon will have receded enough that it will no longer be able to completely cover the Sun. It will pass directly in front of it, but it will appear as a smaller, dark disk silhouetted against a brilliant ring of sunlight. These annular eclipses are beautiful in their own right, but they lack the breathtaking totality, the sudden daytime darkness, and the chance to see the Sun's corona. The age of the total solar eclipse will have passed. Looking even further ahead, billions of years from now, the Earth-Moon system will eventually reach a stable final state. The Moon will stop receding when Earth's rotation has slowed to match the Moon's orbital period. At that point, a single day on Earth would last as long as a single month is today about 47 of our current days. Our planet and its Moon would be locked in a gravitational embrace, forever facing one another, with the Moon only visible from one hemisphere of Earth. This slow, celestial waltz is a powerful reminder that even the most seemingly permanent features of our sky are part of a dynamic and ever-evolving universe. The clock is ticking, not just for us, but for the very rhythm of our world. But just as we find ourselves connected to distant particles through entanglement, we must also confront the staggering reality of cosmic emptiness on a scale that is almost impossible to fathom. If you were to point a telescope toward the constellation of Boötes, the herdsman, you would be aiming at one of the most desolate places in the entire known universe, the Boötes Void. This is not merely an empty patch of sky. It is a colossal spherical region of space so vast that it defies comprehension, stretching an incredible 330 million light-years across. This void is a gaping hole in the cosmic web, a universe within a universe, but one that is hauntingly empty. To grasp the scale, consider that our entire Milky Way galaxy is a mere 100,000 light-years from end to end. You could line up over 3,000 Milky Way galaxies side by side, and they would still not span the diameter of this void. If our solar system were located at its center, the night sky would be virtually black. We wouldn't have discovered other galaxies until the 1960s because the nearest one would be impossibly far away. The existence of such a void was completely unexpected. When astronomer Robert Kirshner and his team first identified it in the 1980s, it challenged everything we thought we knew about the distribution of matter in the cosmos. The prevailing model suggested that matter should be spread somewhat evenly, like raisins in that rising bread dough. But the Boötes Void revealed that the cosmos has a foam-like structure, with immense filaments and sheets of galaxies woven around correspondingly immense empty bubbles. This is the cosmic web in its full glory, and voids are the empty spaces within that web. What makes the Boötes Void so particularly mysterious isn't just its size, but its profound emptiness. Initially, it was thought to contain almost no galaxies at all, earning it the nickname the Great Nothing. Subsequent, more sensitive surveys have found a handful, perhaps 60 galaxies scattered throughout that unimaginable volume, where based on the average density of the universe, there should be thousands. Imagine a ball large enough to hold every star you can see on a clear night, and then filling that entire ball with just a few dozen specks of light, separated by millions of light-years of perfect darkness. That is the isolation of the Boötes Void. So how does such a thing form? the leading theory points back to the very earliest moments of the universe, to a time of cosmic inflation. Tiny quantum fluctuations in that primordial energy field were stretched to enormous sizes, creating slight overdensities and underdensities in the distribution of matter. Over billions of years, gravity acted as an amplifier. The slightly denser regions pulled in more and more matter, eventually collapsing into the galaxies and clusters we see in the filaments. The underdense regions, meanwhile, were left behind. The matter they contained was siphoned away by the gravitational pull of the surrounding denser structures, evacuating these spaces and creating the vast voids we observe today. In a sense, the Boötes Void is not an active emptiness, but a relic of a process of cosmic drainage that has been ongoing for over 13 billion years. The galaxies that do remain inside the void are fascinating in their own right. They are often isolated, lonely, field galaxies that have evolved in near-total seclusion, cut off from the frequent galactic collisions and interactions that drive star formation and evolution in the crowded clusters. Studying these isolated islands can tell us a great deal about how a galaxy develops when left entirely to its own devices, without the influence of its neighbors. The existence of the Boötes Void and others like it forces a profound shift in perspective. We often focus on the bright, dense nodes of the cosmic web, the glittering galaxies and brilliant quasars. But the voids are the true architectural backbone of the universe, making up the overwhelming majority of its volume. They are the negative space that defines the positive, the silence between the notes that gives the cosmic symphony its structure and form. They remind us that the universe is not just a collection of objects, but a complex hierarchical tapestry where emptiness is just as fundamental to its character as the light. Now, as we continue to probe the fundamental nature of reality, we arrive at a truth that is so counterintuitive it seems to defy all common sense, yet it forms the very bedrock of our modern technological world. Light, the very essence of vision and the messenger of the cosmos, is not one thing or the other. It is both a particle and a wave simultaneously. This wave-particle duality isn't just a quirky fact. It is a fundamental property of all matter and energy at the quantum scale, and it completely shatters our classical, everyday understanding of what an object is. We are used to things being clearly defined. A baseball is a solid particle. You can throw it and catch it in a specific location. A ripple in a pond is a wave. It's spread out, it interferes with other ripples, and it can bend around obstacles. Our intuition tells us something must be one or the other, but light stubbornly refuses to be pigeonholed. For centuries, giants of science debated its true nature. Isaac Newton championed the corpuscular theory, arguing that light was composed of tiny particles. Around the same time, Christian Huygens proposed that light was a wave much like sound. For a long time, the wave theory seemed to win out, thanks to beautiful experiments demonstrating interference and diffraction, unmistakably wave-like behaviors. For instance, when light passes through two closely spaced slits, it doesn't just create two bright spots on a screen behind it. Instead, it produces a series of light and dark bands, an interference pattern. This happens because the light waves emanating from the two slits spread out and overlap. Where the peaks of the waves meet, they reinforce each other, creating a bright band. Where a peak meets a trough, they cancel each other out, leaving darkness. This is classic wave behavior. But then, in the early 20th century, a series of discoveries, particularly the photoelectric effect explained by Albert Einstein, threw a wrench in the works. The photoelectric effect showed that when light shines on certain metals, it can knock electrons loose. But the strange part was that the energy of the ejected electrons didn't depend on the brightness of the light, but on its color, its frequency. Increasing the intensity of a red light, no matter how bright, would never eject an electron, while even a very dim blue light would. This made no sense if light were a continuous wave. A more intense wave should simply transfer more energy. Einstein's brilliant solution was to propose that light energy arrives in little, discrete packets or quanta, which we now call photons. In this view, each photon is like a tiny particle carrying a specific amount of energy proportional to its frequency. A single photon of blue light has enough energy to knock an electron loose, whereas a photon of red light does not. Increasing the brightness just means more photons, not more energetic ones. So, which is it? Is light a wave or a particle? The breathtaking answer from quantum mechanics is, it depends on how you choose to look at it. The ultimate demonstration of this bizarre duality is the famous double-slit experiment, performed not just with light, but with electrons, atoms, and even large molecules. And its results are nothing short of miraculous. When you fire a beam of light at a barrier with two slits, you get that beautiful wave-like interference pattern on the detector screen. Now, let's take it a step further. What if we fire the photons one at a time with a significant delay between each one? Common sense says each photon, as a particle, should go through one slit or the other and create two simple clusters on the screen directly behind the slits. But that is not what happens, even when you send photons through one by one, so they can't possibly be interfering with each other. The interference pattern still slowly builds up over time. It's as if each individual photon is passing through both slits at once, interfering with itself. The single photon is behaving as a spread-out wave that explores both paths simultaneously. This is the heart of quantum superposition, but the real magic, the part that truly rattles our sense of reality, happens when you try to catch the photon in the act. If you place a detector at the slits to determine which path each photon actually takes, the interference pattern instantly vanishes. The moment you force the photon to declare its location, to behave like a localized particle, the wave-like behavior disappears and you're left with just two clusters on the screen. The simple act of observation, of measurement, collapses the photon's wave function, forcing it to choose a single, concrete reality. It's as if the photon knows it's being watched and changes its behavior accordingly. This has staggering implications. It suggests that at the most fundamental level, objects do not have definite properties until they are measured. Light is neither a wave nor a particle in a fixed sense. Its nature is contextual, defined by its interaction with the world. This duality is not a flaw in our understanding. It is a profound feature of the universe, a feature that is harnessed in technologies like electron microscopes and is the basis for the emerging field of quantum computing. It forces us to accept that the clear, deterministic reality we experience every day is an emergent illusion, a special case that arises from the collective behavior of countless quantum systems. Beneath the surface, the universe operates on a set of rules where a single thing can be in two places at once, can be both spread out and localized, and where the observer is inextricably linked to the outcome. And now, let's correct one of the most persistent and charming misconceptions in all of astronomy, a truth about the very heart of our solar system that we see with our own eyes every single day. Ask anyone to pick up a crayon and draw the sun, and they will almost certainly reach for a brilliant shade of yellow. It seems like an undeniable fact written right across the sky. But the reality is, the sun is not yellow. From the pristine vantage point of space above our distorting atmosphere, the sun is a brilliant, piercing white. This fact isn't just a trivial correction. It reveals the fascinating physics of light, the clever adaptations of our own vision, and the transformative effect our planet's thin blue blanket has on everything we see. So, why does our star appear to bathe the world in golden light? The answer lies not in the sun itself, but in the air all around us. Earth's atmosphere is filled with countless tiny molecules of nitrogen and oxygen, and when sunlight enters this gaseous sea, a remarkable filtering process begins. This phenomenon is known as Rayleigh scattering. The shorter wavelengths of light, the blues and violets, interact much more strongly with these tiny molecules than the longer wavelengths, like reds and oranges. Think of it like this: the blue light is like a tiny, bouncy ball thrown into a room full of pillars. It ricochets and scatters in every direction. The red light, however, is like a large, heavy ball that barrels straight through, largely unaffected. So, as sunlight travels through tens of miles of atmosphere, the blue light is scattered away from its original path, bouncing around the sky and ultimately reaching our eyes from all directions. This is precisely why the sky appears blue during the day. We're not seeing the direct, unscattered light from the sun. We're seeing the blue light that has been redirected across the entire dome of the sky. But this scattering has a direct and complementary effect on the sun itself. If the blue light is being removed from the direct beam of sunlight and scattered across the sky, what's left in that direct beam? The longer wavelengths, the yellows, oranges, and reds. By the time the sun's light finishes its journey through the atmosphere and reaches your eyes, it has been subtly filtered, stripped of a significant portion of its blue component. This is why the sun's disk appears yellow to us on the ground. The effect becomes even more dramatic at sunrise and sunset, when the sun is low on the horizon. At those times, sunlight has to travel through a much thicker slice of atmosphere to reach you. This extended journey scatters away even more of the blue and green light, leaving behind a richer, deeper palette of fiery reds, oranges, and brilliant golds. So, the magnificent colors of a sunset are essentially the atmosphere acting as a colossal, dynamic filter, presenting us with a beautiful but technically altered view of our star. Now, if you could take a spaceship and ascend above the atmosphere, you would see the sun for what it truly is, a blindingly bright white orb. This whiteness is the result of the sun emitting light across the entire visible spectrum, and in a combination that our brains perceive as neutral white. In fact, if we analyze the sun's spectrum in detail, we find something even more intriguing. The peak intensity of the light emitted by the sun's surface actually falls within the green portion of the spectrum. This often leads to a follow-up question. If the sun's light peaks in the green, why doesn't it look green? The answer is a wonderful demonstration of how our vision and our brains work. We don't perceive color based on a single peak wavelength alone. Our eyes have 3 different types of color receptors for red, green, and blue, and our brain interprets color based on the combination of signals from all 3. The sun emits a very broad and continuous range of colors, from deep red through violet. The combination of all these colors, with a strong contribution from the green peak, but balanced by significant amounts of red and blue light, mixes together to create a sensation we interpret as white. Our visual system is exquisitely calibrated to sunlight. We evolved under this particular blend of wavelengths, so our brain defines this specific mixture as neutral white. It's the standard against which we judge all other colors, so the next time you step outside on a clear day and glance up at that familiar golden disk, you can appreciate the complex physics at play. You are witnessing a collaborative masterpiece between the universe and our planet. The sun provides the raw, white light, and Earth's atmosphere sculpts it, painting the sky blue and the sun yellow, creating the vibrant, life-filled world of color we are so fortunate to call home. Now, let's turn our attention from the vast emptiness of cosmic voids to a persistent mystery right here in our own solar system. For centuries, we've mapped the planets orbiting our sun, believing our celestial family was complete. But what if we were wrong? There is compelling, though still circumstantial, evidence that a true 9th planet, a massive, unseen world, may be lurking in the frozen, dark reaches far beyond Neptune, silently shaping the orbits of distant icy bodies from the shadows. This isn't the reclassification of Pluto we're talking about. This is the potential discovery of a new giant, a planet with a mass several times that of Earth, orbiting so far away that it has eluded our telescopes for so long. The primary clue for this hidden world comes not from seeing it directly, but from observing its gravitational influence on a population of small, icy objects in the distant Kuiper belt. The Kuiper belt is a vast disk of frozen remnants left over from the solar system's formation, extending out beyond the orbit of Neptune. Within this belt, there is a group of objects known as extreme trans-Neptunian objects, or ETNOs, whose orbits are profoundly strange. They are highly elongated, taking them incredibly far from the Sun. But the peculiar part isn't just their stretched-out paths, it's how these paths are oriented in space. The orbits of these distant objects appear to be clustered. Their points of closest approach to the Sun, their perihelia, are grouped together in the same general region of the solar system, and their orbits are tilted in a similar direction. This is statistically very unusual. Imagine a busy roundabout with cars entering and exiting at all points randomly. Now imagine you observe that a specific group of cars, despite coming from different directions, all choose to exit at exactly the same exit, and their paths are all tilted at a similar angle as they do so. You would start to suspect there was a reason, perhaps a new road sign or a powerful magnet pulling them that way. In the case of these Kuiper belt objects, the gravitational pull of a massive, distant planet is the leading suspect for that organizing force. The hypothetical planet 9, with an estimated mass of 5 to 10 times that of Earth, would have a tremendous gravitational reach. As it moves along its own slow, wide orbit, which could take 10 to 20,000 years to complete a single trip around the Sun, its gravity would act like a shepherd, herding these smaller objects into orbits that remain stable and clustered relative to its own position. Their peculiar alignments are precisely what astronomers would expect to see if a large planet were gravitationally corralling them over billions of years. The hunt for this world is one of the great modern astronomical detective stories. Researchers are using some of the most powerful telescopes on Earth, like the Subaru telescope in Hawaii, to painstakingly scan the vast swaths of sky where the planet is predicted to be. The challenge is immense. At such a great distance, perhaps 400 to 800 times farther from the Sun than Earth is, Planet 9 would receive virtually no sunlight. It would be exceptionally faint, moving incredibly slowly against the background stars, a dim ghost in an already dark sky. Compounding the difficulty is the fact that its exact orbit is unknown. Astronomers have a general idea of where to look based on the orbital clustering, but they must search a massive potential area, like finding a single specific grain of sand on a beach by methodically scanning it with a magnifying glass. Beyond the orbital clustering, other solar system anomalies might also be explained by Planet 9's presence. For instance, the entire plane of the solar system is tilted by about 6 degrees relative to the Sun's equator. A massive, inclined orbit for Planet 9 could provide the gravitational leverage to torque the entire system into this misaligned state. There's even speculation that such a world could be a captured exoplanet, an orphan from another star system that was gravitationally snatched by our Sun in its youth, making it a permanent, yet hidden, immigrant in our own cosmic neighborhood. Of course, the scientific community remains cautious. Some researchers propose that the observed clustering could be the result of observational bias, since it's inherently difficult to discover these incredibly distant objects, and our current surveys might be inadvertently looking in the right places to see a pattern that isn't truly there. The only way to settle the debate is to find the planet itself. The potential discovery of Planet 9 would be a monumental event, a reminder that our exploration of the solar system is far from over. It would rewrite astronomy textbooks and force us to reconsider the dynamics and formation history of our own cosmic backyard. It represents the thrilling possibility that a new world of immense proportions is still waiting to be found, not in some distant star system, but right here, hidden in the perpetual twilight at the frontier of everything we call home. Following this journey across the vast scales of our solar system and the strange quantum realm, we arrive at a truth about the shape of the cosmos itself, a geometric property so fundamental it dictates the ultimate destiny of everything. When cosmologists announce that the universe is flat, they are not describing a two-dimensional pancake like a sheet of paper floating in nothingness. Instead, they are describing the intrinsic geometry of space-time on the largest imaginable scales, the rules that govern how parallel beams of light behave as they travel across billions of light years. In a flat universe, the familiar rules of Euclidean geometry we learned in school hold true. Two laser beams fired perfectly parallel to each other will remain parallel forever, never converging or diverging. This geometry is a direct consequence of the precise density of the universe, a perfect balancing act between the energy that drives expansion and the gravitational pull of all matter and dark matter trying to rein it in. This critical density creates a cosmos where space-time itself is neither positively curved like the surface of a sphere nor negatively curved like a saddle, but is, for all intents and purposes, straight and flat. The evidence for this monumental conclusion comes from the oldest light we can see, the cosmic microwave background radiation. This afterglow from the Big Bang is a snapshot of the infant universe, a time when it was just 380,000 years old, and it is imprinted with incredibly subtle patterns of hot and cold spots. These tiny temperature fluctuations are the seeds of all future structure, the galaxies and clusters we see today. By meticulously measuring the apparent size of these spots on the sky, satellites like Planck and WMAP have been able to act as cosmic surveyors. Think of it like this: the spots have a known physical size based on how far sound waves could travel in the early plasma. By measuring how big these spots appear to us from our vantage point billions of years later, we can deduce the geometry of the intervening space. If the universe were positively curved like the surface of a globe, light rays would converge, making the spots appear larger than they truly are. If it were negatively curved like a saddle, light rays would diverge, making the spots seem smaller. The exquisite measurements show, with stunning precision, that the spots appear exactly the size predicted for a perfectly flat universe. The light has traveled in straight lines across the eons, confirming that our cosmos is built on a Euclidean foundation. This geometric flatness has profound implications for the universe's final fate. A flat universe sits precisely on the dividing line between two other dramatic possibilities. A positively curved, closed universe would eventually halt its expansion and collapse back in a big crunch, a fiery reversal of the Big Bang. A negatively curved, open universe would expand forever at a rapid pace, its galaxies tearing apart in a big rip. Our flat universe, however, is destined for a different, more gradual end. It will continue to expand forever, but at an ever-slowing rate that asymptotically approaches zero. Of course, we know that dark energy is currently causing an acceleration in this expansion, but even with that mysterious force at work, the flat geometry indicates that the total energy density of the cosmos is just right to keep it on this knife's edge. This leads to a perpetual, slow expansion, a future where the universe will simply become colder, darker, and more diffuse over trillions of years, culminating in the heat death where all usable energy is finally exhausted. The fact that we live in a flat universe feels like an incredible coincidence, a perfect tuning of the cosmic ledger that begs for an explanation. Why is the density so exquisitely balanced? The most compelling answer comes from the theory of cosmic inflation, which proposes that a fraction of a second after the beginning, the universe underwent a brief period of exponential expansion. This inflationary burst would have stretched the fabric of space-time so dramatically that any initial curvature would have been flattened out, just as inflating a balloon makes a tiny patch of its surface appear flatter and flatter. Our entire observable universe could be just a tiny, flat patch within a much larger and possibly curved multiverse. So, the simple statement that the universe is flat is far from simple. It is a testament to a profound balance in the cosmos, a geometric signature left over from its most violent beginnings, and a quiet decree for a long, slow, and isolated future. And just when you think you've grasped the rhythm of our solar system, our nearest planetary neighbor presents us with a temporal paradox so strange it seems to defy the very logic of timekeeping. On Venus, a single day lasts longer than an entire year. Let that sink in for a moment. The planet takes 243 Earth days to complete one full rotation on its axis. That's one Venusian day. But it only takes 225 Earth days to complete one full orbit around the Sun. That's one Venusian year. This means that if you were standing on the scorching surface of Venus, the time from one sunrise to the next would be longer than the time it takes the planet to complete its entire journey around our star. To make this cosmic oddity even more bizarre, the Sun on Venus doesn't rise in the east and set in the west as it does here. It does the exact opposite, rising in the west and setting in the east because Venus rotates backwards. This retrograde rotation, combined with its incredibly slow spin, creates a reality where the cosmic cycles we take for granted are completely upended. So, how did Venus become such an astronomical rebel? The leading theory points to a tumultuous early history shaped by gravitational tugs of war and a profoundly transformative atmosphere. In the chaotic early solar system, planets were still settling into their orbits, and gravitational interactions were far more common and violent. Many planetary scientists believe that Venus's original rotation was likely prograde, spinning in the same direction as the other planets. However, the immense gravitational influence of the Sun, combined with the possibility of a colossal collision with another large protoplanetary body, could have literally flipped the planet upside down or severely torqued its spin, setting it on its slow, backward path. Think of it like a spinning top that gets a hard, glancing blow from another object. Its spin can dramatically slow, wobble, and even reverse direction. But the story doesn't end with a single ancient event. The primary culprit responsible for maintaining this glacial pace today is Venus's incredibly thick and heavy atmosphere. The air on Venus is not the gentle, breathable blanket we have on Earth. It is a supercritical fluid of carbon dioxide, with pressures 92 times greater than what we experience at sea level, and it's laced with clouds of sulfuric acid. This massive, dense atmosphere creates an immense amount of friction against the planet's surface, especially as it interacts with mountain ranges. Furthermore, the gravitational pull from the Sun creates strong atmospheric tides. Unlike the gravitational tides that affect Earth's oceans, these are tides in the atmosphere itself. The Sun's gravity tugs on Venus's incredibly thick air, creating a bulge that travels across the planet. This atmospheric bulge has significant mass, and its interaction with the solid ground below acts like a perpetual brake, sapping angular momentum from the planet's rotation and slowing its spin over billions of years. It's a phenomenon known as tidal locking, though in this case it hasn't yet reached a complete lock. The result is a world where the link between the ground and the sky is almost completely broken. The solid body of the planet rotates at one painfully slow speed, while the upper atmosphere, caught in a phenomenon called superrotation, screams around the planet at speeds of over 200 miles per hour, completing a full circuit of the planet in just 4 Earth days. This means the winds in the upper atmosphere of Venus move 60 times faster than the planet itself rotates. If you were floating in those upper cloud decks, you would experience a day dictated by the whipping winds, not the sluggish rotation of the ground far below. This bizarre situation makes Venus a fascinating laboratory for understanding planetary evolution. It shows us that a planet's history is not just written in its rocks and orbit, but also in the dynamic and powerful interplay between its surface and its sky. The fate of a world can be dramatically altered by the weight of its own air. But this cosmic perspective, filled with voids and distant giants, might make our own world feel like a tiny speck. And yet, this next truth reveals that our small planet holds a numerical abundance that can stand against the grand scale of the galaxy itself. on our world, there are more trees than there are stars in our entire Milky Way galaxy. Let's put some staggering numbers to that claim. The most comprehensive scientific studies, combining satellite imagery with ground-level surveys, estimate that Earth is home to over 3 trillion trees. That's a 3 followed by 12 zeros. Now look up at the Milky Way on a clear night. That river of light, containing everything from our sun to the most distant stellar nurseries, is estimated to hold between 100 billion and 400 billion stars. Even at the highest estimate for the galaxy and the lowest for the trees, our planet's arboreal population outnumbers the stellar one by a significant margin. This isn't just a fun piece of trivia. It's a profound statement about the unique, vibrant, and wildly generative nature of a living world when compared to the vast but largely sterile expanse of interstellar space. Think about what a star is, a colossal, self-gravitating sphere of plasma, fusing hydrogen into helium in a process that can last for billions of years. It is a magnificent engine of light and energy, but it is, by its very nature, a solitary titan. A tree, on the other hand, is a complex biological marvel, a hub in an intricate web of life. It interacts with the soil, the atmosphere, and countless other organisms. It provides habitat, produces oxygen, stores carbon, and cycles water. While a star represents immense physical power, a tree represents the profound complexity and interconnectedness of a biosphere. This comparison becomes even more striking when you consider the relative scales involved. Our entire planet is an infinitesimal dot compared to the volume of the Milky Way. If the galaxy were the size of the entire continent of Asia, Earth would be smaller than a single grain of sand on a beach in Japan. And yet, within that microscopic speck of a world, life has managed to proliferate to such an extraordinary degree that it can outnumber, in one specific category, all the suns in that continent-sized galaxy. It speaks to the incredible fecundity and tenacity of life. Of course, it's crucial to add a sobering note to this awe-inspiring fact. That number of 3 trillion trees is not a static figure, and it is also a fraction of what once was. Since the dawn of human civilization, it's estimated that the global number of trees has been nearly cut in half. We are losing billions of trees each year to deforestation, urban expansion, and agricultural development. So, while the statistic is a testament to the power of life, it is also a fragile one, a reminder of the responsibility that comes with being the custodians of such a vibrant and unique world in a cosmos where true, complex life may be exceptionally rare. This juxtaposition, the abundance of trees on our tiny world versus the number of stars in our vast galaxy, ultimately reframes our place in the cosmos. We are not just inhabitants of a random rock orbiting an average star. We are residents of a planet that is teeming with life on a scale that can literally compete with the grandest structures we see in the night sky. It grounds the cosmic perspective, reminding us that while we gaze in wonder at the stars, we are walking every day through a forest of billions upon billions of living wonders right here at home. And just as we contemplate the immense scale of our own galaxy and its countless stars, we are forced to confront a humbling reality. Our entire Milky Way is not a stationary island in the cosmos. It is a ship adrift on a vast cosmic current, being pulled inexorably toward a mysterious and unseen destination. For decades, astronomers have known that our galaxy is moving through space at a staggering speed of over 2 million kilometers per hour relative to the afterglow of the Big Bang. But the question was, where is it going? The answer led to the discovery of one of the most profound gravitational mysteries in our cosmic neighborhood, the Great Attractor. This isn't a single object, but a colossal concentration of mass, a gravitational focal point located in the general direction of the constellations Centaurus and Hydra, roughly 150 million light-years away. The sheer pull of this region is so immense that it is drawing not only our own Milky Way, but also the entire local group of galaxies and thousands of other galaxies in our supercluster, all flowing downstream in a vast cosmic river toward this one point in space. Imagine a slow-motion waterfall on a universal scale, with galaxies of all shapes and sizes all moving in the same general direction, caught in the grip of a gravity well we cannot directly see. And that is the central puzzle. The Great Attractor lies directly behind the plane of our own Milky Way, in a zone of the sky we call the zone of avoidance. This region is obscured by thick clouds of gas and dust and the sheer density of stars in the disk of our own galaxy. It's like trying to see a distant mountain range through a dense perpetual fog bank. For a long time, this hidden realm was a complete blind spot in our maps of the universe. The initial discovery came not from seeing the attractor itself, but from meticulously mapping the peculiar velocities of galaxies, how they move relative to the overall expansion of the universe. When astronomers did this, they found a consistent and unsettling flow. A vast swath of the universe around us was deviating from the smooth Hubble expansion, all being tugged toward this one hidden point. It was as if we were living on a slope, and everything was slowly sliding toward a valley we couldn't see. For years, the nature of this hidden mass remained speculative. Was it a single, unfathomably large object? A supercluster of galaxies? Further observations, particularly in X-ray and radio wavelengths that can pierce through the galactic dust, have begun to lift the veil. We now understand that the Great Attractor is part of an even larger structure, the Laniakea supercluster. Laniakea, which means immense heaven in Hawaiian, is a cosmic filament containing over 100,000 galaxies, and the Great Attractor sits at its heart, acting as the central gravitational anchor for this entire metropolis of galaxies. Our own Milky Way resides on the outskirts of this vast structure, a suburban galaxy on the edge of a sprawling galactic city, but the story doesn't even end there. The pull we feel isn't just from the Great Attractor alone. Beyond it lies something even more massive and distant, known as the Shapley supercluster, the most massive concentration of galaxies in our nearby universe. It is likely that the Shapley supercluster is itself tugging on the Great Attractor, which in turn is pulling us. So our journey is part of a cosmic chain of gravitational influence, a relay race of pulls across hundreds of millions of light years. This grand motion puts our place in the universe into a startling new perspective. We are not merely expanding outward from a big bang. We are also engaged in an intricate, local dance governed by the uneven distribution of matter on the grandest scales. The empty voids and dense superclusters create a cosmic topography of hills and valleys in the fabric of space-time, and we are flowing down one of these slopes. It is a powerful reminder that the force of gravity knows no boundaries, orchestrating the motion of galaxies across mind-numbing distances and revealing a universe that is dynamic, interconnected, and full of hidden wonders still waiting to be uncovered. While you sit reading this, an invisible blizzard of cosmic ghosts is passing straight through you, right through the chair you're sitting on, and even through the solid rock of the earth beneath your feet. These are neutrinos, nature's most elusive particles, and they are so ethereal that trillions of them stream through your body every single second without you ever feeling a thing. The vast majority of these ghostly visitors come from our very own sun, produced in the heart of its nuclear furnace. In the core of the sun, where the pressure and temperature are staggering, protons fuse together to form helium nuclei. This fusion process doesn't just release the sunlight that powers our world, it also releases a torrent of neutrinos. In fact, for every single fusion reaction that occurs, a neutrino is born and immediately escapes the sun at nearly the speed of light, carrying away a tiny bit of energy. The numbers involved are almost impossible to comprehend. The sun is so prolific a neutrino factory that about 100 billion of them pass through the thumbnail on your finger every second. That's more neutrinos than there are stars in the entire observable universe streaming through a tiny patch of your body in the blink of an eye. and the Sun is just one source. Neutrinos are also produced in colossal quantities during supernova explosions, in the violent environments around black holes, and even in the upper atmosphere when cosmic rays slam into air molecules. So why don't we notice this constant, silent storm? It all comes down to one of their defining characteristics. They barely interact with anything. Neutrinos are neutral particles, meaning they have no electric charge. They are affected only by the weak nuclear force and gravity, and the weak force has an incredibly short range. This makes neutrinos the ultimate introverts of the particle world. They simply refuse to shake hands with normal matter. To a neutrino, the solid world you and I experience is almost entirely empty space. The atoms that make up your body are vast, sprawling cathedrals of nothingness from a neutrino's perspective. The nucleus of an atom is a tiny speck at the center, and the electrons are even smaller specks whirling around it at a great distance. A neutrino can fly through light years of lead, a distance spanning trillions upon trillions of miles of solid metal, with only a 50% chance of hitting a single atomic nucleus. This is why building a neutrino detector is one of the most challenging tasks in all of experimental physics. You can't just catch them in a bottle. Instead, scientists have to build enormous, exquisitely sensitive instruments deep underground to shield them from other distracting cosmic rays. The most famous of these is perhaps the Super Kamiok and detector in Japan, a tank filled with 50,000 tons of ultra-pure water, buried 1 kilometer beneath a mountain. Lining the tank are over 13,000 light-sensitive bulbs. On the incredibly rare occasion that a neutrino does interact with an atom in the water, it produces a tiny, faster-than-light flash of blue light called Cherenkov radiation. By detecting these faint, beautiful flashes, scientists can study the properties of these cosmic phantoms. The very existence of neutrinos was first proposed by Wolfgang Pauli in 1930 to solve a crisis in physics. Scientists studying a type of radioactive decay called beta decay found that energy seemed to be missing from the reaction, violating the sacred principle of energy conservation. Pauli reluctantly suggested that an unseen, neutral particle must be carrying the missing energy away. He famously said, "I have done a terrible thing. I have postulated a particle that cannot be detected." He was almost right. It took another 26 years before neutrinos were directly detected. Today, we know they are not just one particle, but come in 3 different types or flavors: the electron neutrino, the muon neutrino, and the tau neutrino, and they can oscillate or change from one flavor to another as they travel. This surprising discovery, which earned the Nobel Prize in Physics in 2015, proved that neutrinos have a tiny amount of mass, a finding that forced a revision of the standard model of particle physics. So the next time you feel alone, remember that you are at the center of an unimaginably dense, silent, and constant rain. You are being perpetually threaded by the ghosts of the sun's core, by the echoes of distant stellar explosions, and by the faint whispers of the universe's most abundant particles after photons. You are a temporary, living constellation in a universe that is, in a very real sense, passing right through you. But while our planet is hurtling through space and bathed in a cosmic wind, its very shape reveals another profound truth about the dynamic nature of our world. Despite what every classroom globe and textbook illustration might lead you to believe, the Earth is not a perfect sphere. It is an oblate spheroid, which is a sophisticated way of saying it's slightly squashed, bulging out around its middle like a person who has enjoyed one too many large meals. This equatorial bulge is not a flaw in creation. It is a direct and beautiful consequence of our planet's relentless spin. Imagine our young, molten Earth just after its formation, a massive ball of rock and magma beginning to rotate. As it spun, the material at the equator experienced the strongest centrifugal force, a kind of outward push that acted against gravity's inward pull. This caused the planet's pliable form to gradually distort, with matter migrating from the poles toward the equator, creating a permanent bulge. The result is a world where the diameter measured from one point on the equator to its opposite is about 27 miles or 43 kilometers, longer than the diameter measured from the North Pole to the South Pole. To put that in perspective, if you shrunk the Earth down to the size of a standard basketball, the variation would be so tiny, so minuscule, that the ball would feel perfectly smooth to your hand. Yet on the planetary scale, this subtle flattening has very real and measurable consequences for life and science. One of the most tangible effects is on your own weight. Because the equator is farther from the Earth's center than the poles are, the gravitational pull you experience there is slightly weaker. Furthermore, the centrifugal force from the planet's rotation is strongest at the equator, providing a tiny outward push that further counteracts gravity. Combined, these two factors mean that if you were to step on a scale at the equator, you would weigh roughly 0.5% less than you would at either pole. For a person weighing 180 pounds, that's nearly a whole pound lighter just by traveling to a different latitude. This isn't a change in your mass, but a change in the gravitational force acting upon you. This shape is far from a static fact. It is a living testament to the powerful forces that are constantly, though imperceptibly, shaping our planet. The Earth's rotation is a sculptor, and the oblate form is its masterpiece. This knowledge is absolutely critical for the modern world, especially for the precision required by global positioning systems. The satellites in the GPS network have their orbits meticulously calculated based on our planet's true, bulging shape. If their software models assumed Earth was a perfect sphere, their calculated positions would drift by hundreds of meters, rendering turn-by-turn navigation on your phone completely useless within minutes. The bulge even influences our climate and ocean currents. The fact that the sun's rays hit the bulging equator more directly than the flattened poles is the fundamental driver of all weather on Earth, creating the temperature difference that powers atmospheric circulation and ultimately the great currents of the oceans. So, the next time you see a picture of our beautiful blue marble from space, remember that you are not looking at a perfect orb. You are seeing a dynamic, spinning world, a celestial body whose very form is a permanent record of the powerful, invisible forces that have been molding it since the very beginning. Just as our own planet has a baseline temperature, so too does the cosmos itself. The entire universe is bathed in a faint, cold glow, a relic from its earliest moments that permeates every single cubic inch of space. This is the cosmic microwave background radiation, and it has a uniform temperature of just 2.7 degrees above absolute zero. To find the origin of this universal chill, we have to journey back to a time when the universe was anything but cold. In the first few 100,000 years after the Big Bang, the cosmos was an opaque, seething soup of plasma, so dense and hot that light couldn't travel freely. Photons were constantly bouncing off free electrons, trapped in a relentless pinball game. But as the universe expanded and cooled, it eventually reached a critical temperature, about 3,000 degrees Celsius, where electrons could combine with protons to form the first stable hydrogen atoms. This pivotal moment is known as recombination. Suddenly, the fog cleared. With most of the charged electrons now locked into neutral atoms, the photons, which had been trapped for eons, were finally set free. They began streaming across the universe in every direction, and this first flash of liberated light is what we detect today as the cosmic microwave background. Imagine a cosmic photo album, and this is the very first baby picture of the universe, taken when it was just 380,000 years old. But if the universe was 3,000 degrees back then, why is the radiation now only 2.7 degrees above absolute zero? The answer lies in the relentless expansion of space itself over the past 13.8 billion years. As the universe stretched, it also stretched the wavelength of that primordial light. The short, energetic wavelengths of visible light and ultraviolet radiation have been stretched so dramatically that they have been shifted all the way down the electromagnetic spectrum into the microwave region. This process, called cosmological redshift, is directly analogous to the cooling of a gas. When you let a gas expand, it cools down. The universe has been expanding for billions of years, and in doing so, it has cooled the once searing afterglow down to a mere whisper of heat. The discovery of this radiation in 1964 by Arno Penzias and Robert Wilson was one of the greatest accidental breakthroughs in scientific history. They were using a large radio antenna, and no matter where they pointed it, they found a persistent, uniform hiss that they couldn't eliminate, even after cleaning out pigeon nests from the dish. This annoying noise, present in every direction, turned out to be the most important signal in all of cosmology, the direct echo of creation itself. It was the smoking gun evidence that confirmed the Big Bang theory and earned them a Nobel Prize. The CMB is remarkably, almost perfectly uniform. No matter where you look in the sky, the temperature is the same to within a few hundred thousandths of a degree. This incredible smoothness was a major puzzle for cosmologists. How could regions of the universe on opposite sides of the sky, which could never have been in thermal contact with each other, have the exact same temperature? The leading solution is the theory of cosmic inflation, which proposes that the universe underwent a period of exponential expansion in its first fraction of a second, stretching a tiny, homogeneous patch into our entire observable cosmos. Yet, when we look with exquisitely sensitive instruments like the Planck satellite, we find that the CMB is not perfectly smooth. It is imprinted with tiny, tiny fluctuations, anisotropies, variations in temperature of just millionths of a degree. These minute ripples are the cosmic seeds of all structure. They represent the slight over-densities and under-densities in the early universe, the places where gravity had a little more or a little less to work with. Over billions of years, these tiny wrinkles were amplified by gravity. The slightly denser spots pulled in more and more matter, eventually collapsing into the vast cosmic web of galaxies, clusters, and superclusters we see today. The very largest structures in our universe, spanning hundreds of millions of light years, were all mapped out in those first tiny temperature variations. This makes the cosmic microwave background the ultimate cosmic blueprint, a fossilized imprint of the gravitational potential that would one day give rise to every star, planet, and ultimately to us. Studying its precise patterns allows us to read the fundamental parameters of the universe like a recipe, telling us its age, composition, and geometry with stunning precision. So, the next time you see the static snow on an old analog television, know that you're witnessing a small fraction of that signal coming from the cosmic microwave background, the cooled and stretched remains of the universe's fiery birth, a permanent, gentle warmth that fills the entirety of existence. Now, let's turn our attention to a planet that seems to defy the very logic of what a world should be. If you were to embark on the ultimate cosmic plumbing challenge, finding a bathtub large enough to hold our entire solar system, and you began dropping planets in one by one, you would witness something truly miraculous. Saturn, the second largest planet in our neighborhood, would not sink to the bottom with a heavy thud. Instead, this majestic ringed giant would bob gently on the surface, floating like a colossal striated apple. This isn't a trick of magic, it's a direct consequence of Saturn's mind-bogglingly low density. The average density of a planet is its total mass divided by its total volume, a measure of how much stuff is packed into its space. Earth, with its dense core of iron and nickel and its rocky mantle, has an average density of about 5.5 grams per cubic centimeter, which is why it sinks without a trace. Water, by definition, has a density of 1 gram per cubic centimeter. Saturn, astonishingly, has an average density of only 0.69 grams per cubic centimeter. That is less than the density of water. This means that, on average, the entire planet is less dense than the very liquid we float in at the swimming pool. To understand how a planet hundreds of times more massive than Earth can be so light, we need to look at what Saturn is actually made of. Unlike the terrestrial planets like Earth or Mars, which are composed primarily of rock and metal, Saturn is a gas giant. It has no solid surface to stand on. The vast, overwhelming majority of its volume is composed of the two lightest elements in the universe, hydrogen and helium. Imagine a planet that is less of a solid ball and more of a colossal, swirling atmosphere that just gets denser and denser the deeper you go. If you were to try to land on Saturn, you would simply descend through ever-thickening layers of cloud and gas, with the pressure and temperature increasing to unimaginable levels, until the hydrogen around you is compressed into a bizarre, metallic liquid form surrounding a relatively small, hot, and dense core. But that dense core is tiny compared to the planet's immense girth. It's the sheer volume of incredibly lightweight gas that dominates Saturn's overall character, puffing it out to its enormous size while keeping its overall density remarkably low. This unique property makes Saturn the solar system's ultimate cosmic floater, a title it holds alone. Jupiter, while also a gas giant, is more compact and has a stronger gravitational pull, compressing its internal gases to a higher density, just slightly above that of water. Uranus and Neptune, the ice giants, contain a much larger fraction of heavier elements like water, ammonia, and methane ices surrounding their rocky cores, making them significantly denser. So, Saturn sits in a class of its own, a testament to the fact that in the cosmos, size does not always equate to heft. Its beautiful, low-density nature even contributes to its most famous feature, its spectacular ring system. Because Saturn's gravity is comparatively weaker for its size, a direct result of its low overall mass, it was easier for tidal forces to prevent nearby material from clumping together into a moon, or to tear apart a moon that ventured too close. This left a magnificent disk of countless ice and rock particles, all orbiting in a delicate, stable ballet, a visible manifestation of the planet's gentle gravitational hold. So, the next time you gaze at a picture of Saturn with its stunning rings, remember you are not looking at a heavy, solid world. You are seeing a cosmic balloon, a vast and beautiful sphere of predominantly light gas, a planet so insubstantial that, in the grandest of bathtubs, it would simply ride the wave. Yet for all the cosmic structures we can map and the particles we can detect, some of the most common worlds in the galaxy are also the most hidden, drifting in perpetual exile through the freezing darkness between the stars. These are rogue planets, lone wanderers untethered to any sun, cast out from their stellar families to journey forever through the interstellar void. The process that creates these orphaned worlds is as violent as it is common. In the chaotic early days of a young star system, protoplanets jostle for position in the dusty disk surrounding their infant sun. Their gravitational interactions are a complex dance, and sometimes that dance turns into a slingshot. A close encounter with a much larger planet, like a Jupiter, can act as a gravitational catapult, flinging a smaller, Earth-sized world out of the system entirely, severing its bond to its star and setting it on a solitary path into the galactic abyss. Other rogue planets might form on their own in the way stars do, from collapsing clouds of gas and dust that were simply too small to ignite into a sun. The result is the same, a dark, free-floating world adrift in the immense space between stellar neighbors. The scale of this phenomenon is staggering. Based on gravitational microlensing surveys, where the gravity of a foreground object briefly magnifies the light of a distant star, astronomers now estimate there could be billions, perhaps even trillions, of these rogue planets in our Milky Way alone. They might outnumber the stars themselves. This means the dark, empty spaces of our galaxy are not empty at all. They are teeming with unseen worlds, a vast, hidden population of celestial nomads. Picture one of these Earth-like rogue planets. Its surface would be a landscape of profound and permanent night. With no nearby star to provide warmth or light, its surface temperature would plummet to just a few degrees above absolute zero, a deep and unbroken cold that would make the polar regions of our world feel balmy. Any atmosphere it once possessed would have long since frozen solid, collapsing into a blanket of ice on the ground. The only light in the sky would come from the distant, unchanging pinpricks of the galaxy's stars, a static tapestry offering no sunrise, no sunset, and no concept of a day. The surface would be eerily silent, with no wind, no weather, and no liquid water, a frozen geological museum preserving the moment of its expulsion. But here is where the story takes a fascinating turn. Not all hope for life on such a world is necessarily lost. While the surface would be a frozen wasteland, these planets could harbor a secret source of heat deep within their cores. Radioactive elements like uranium and thorium decay over billions of years, generating a steady, if faint, internal warmth. For a large, rocky rogue planet with a thick mantle, this geothermal energy could be enough to maintain a vast subsurface ocean of liquid water, insulated from the frigid void above by a thick crust of ice. It's a scenario reminiscent of Jupiter's moon Europa, but without any star at all. In the pitch-black depths of such an underground sea, sustained solely by planetary heat and chemical energy from hydrothermal vents, life could potentially take hold and persist. Entire ecosystems, completely independent of sunlight, might thrive in these isolated, dark oceans, a testament to life's incredible tenacity. This possibility forces us to radically expand our definition of a habitable world. We are so conditioned to search for planets orbiting within the Goldilocks zone of a star, where temperatures are just right for liquid water. But rogue planets present a completely different paradigm for habitability, one based on internal heat rather than stellar light. They are self-contained biospheres flying solo through the galaxy, potentially carrying their own living cargo across the immense distances between stars. The existence of these wandering worlds also reshapes the story of planet formation. They are the cosmic fallout from the turbulent process of building solar systems, the scattered pieces that didn't make the final cut. Studying their population helps us understand the dynamic and often violent history of our own solar system, revealing that planetary ejection is not a rare fluke, but a common and expected outcome. It suggests that for every stable, orderly system like our own, there are countless lost worlds cast out into the darkness. These solitary travelers are more than just celestial curiosities. They are a haunting reminder of the impermanence of cosmic order and the sheer, overwhelming scale of the galaxy. They are the ghosts of planetary systems past, silent and dark, yet potentially alive in ways we are only beginning to imagine. Looking up at the Andromeda Galaxy on a clear, dark night, it's easy to feel a sense of serene permanence. That faint, smudged patch of light in the constellation bearing its name seems fixed in the heavens, a distant cousin to our own Milky Way. But this placid view is a complete illusion, hiding one of the most dynamic and dramatic truths about our cosmic future. The Andromeda Galaxy is not a static island. It is a colossal ship of stars weighing 1 trillion times the mass of our Sun, and it is on a direct collision course with us, hurtling through the void at an incredible 250,000 miles per hour. This isn't a possibility or a guess, it's a certainty born from meticulous observation. For over a century, astronomers have been able to measure the motion of Andromeda by analyzing the subtle blue shift in its light. While almost every other galaxy we see is flying away from us due to the universe's expansion, Andromeda's light is compressed, shifted toward the blue end of the spectrum. This tells us unequivocally that it is moving toward us, drawn in by the mutual gravitational pull between our two galaxies, a force so powerful it overcomes the expansion of the universe itself. The scale of this impending encounter is almost beyond comprehension. We are separated by 2.5 million light-years of space, a staggering distance, but it is closing fast. In roughly 4 billion years, the two galaxies will begin their first close pass, a gravitational tango that will unfold over billions more years, ultimately resulting in a complete merger. Now, the word collision might conjure images of cosmic car crashes and fiery destruction, but the reality is far more beautiful and less catastrophic than you might think. This will be a merger, not a smash-up. It's crucial to remember what a galaxy is mostly made of: empty space. The average distance between stars in a galaxy is so immense that when two galaxies merge, the stars themselves almost never physically collide. It would be like throwing two handfuls of sand at each other from a mile apart and hoping two individual grains will hit. The real action and the true spectacle is gravitational. As the two galaxies swing past and through each other, their immense collective gravity will act as a cosmic sculptor, warping and twisting their structures beyond recognition. The elegant spiral arms of both the Milky Way and Andromeda will be drawn out into long, streaming tails of stars, gas, and dust, flung into space by immense tidal forces. For any hypothetical observers in that far future, the night sky would transform into something utterly alien and breathtaking. Instead of a familiar band of the Milky Way, the heavens would be dominated by a chaotic, brilliant tapestry. A second giant galaxy would loom ever larger, its structure becoming distorted and mingling with our own. New stars would ignite in brilliant blue bursts as clouds of gas are compressed during the close encounters, lighting up the chaos with the birth of new stellar nurseries. Our own solar system will likely be caught up in this grand rearrangement, while the chances of our sun colliding with another star are vanishingly small. The gravitational tides could easily fling us out of the galactic plane, sending us on a new orbit into the outer halo of the emerging supergalaxy, or perhaps even ejecting us into the intergalactic void altogether. After this prolonged dance, which will involve several close passes over 1 billion or 2 years, the two galaxies will eventually slow, settle, and completely coalesce. The result will be a new, single, giant galaxy. Astronomers have already given this future entity a name, Milkomda. This new galaxy will likely be a vast, elliptical blob of stars, devoid of the beautiful spiral structure of its progenitors. It will be a more sedate, red and dead galaxy where the frenetic star formation of the merger has calmed, leaving behind an older stellar population. This grand event is not unique, it's a standard part of galactic evolution. We see galaxies merging all across the universe, and these collisions are fundamental drivers of growth. Our own Milky Way has cannibalized smaller dwarf galaxies in the past, and it is in the process of absorbing others right now. The merger with Andromeda is simply the next and most monumental step in our galaxy's life story. So, while the thought of two galaxies colliding sounds apocalyptic, it is in fact a creative process. It's a cosmic rebirth, a transformation that will forge a new island universe from the wreckage of the old, a testament to the enduring power of gravity to shape the cosmos on the very largest scales. Now let's shrink that cosmic perspective down to an object of almost unimaginable density. Consider a single sugar cube. You can hold it in your hand, feel its lightness. But what if I told you that a teaspoon's worth of material from a particular kind of cosmic corpse would not weigh a few grams but billions of tons? This isn't a hypothetical substance from science fiction. This is the reality of matter inside a neutron star, one of the most extreme and bizarre objects the universe can create. A neutron star is the collapsed core of a massive star that went supernova. After the outer layers have been blasted into space, if the remaining core is between about 1 and 3 times the mass of our Sun, it doesn't have enough gravity to become a black hole, but it has far too much to remain as a normal star. Instead, it undergoes a collapse so violent and complete that it fundamentally changes what matter is. Imagine taking an object with the mass of our entire Sun, a sphere so large you could fit over 1 million Earths inside it, and crushing it down until it's only about the size of a city, roughly 12 miles across. The forces involved in this collapse are so titanic that they overcome the very atomic forces that give matter its structure. In a normal atom, you have a tiny, dense nucleus surrounded by a vast cloud of electrons, with empty space making up over 99% of the atom's volume. In a neutron star, this empty space is utterly eliminated. The immense gravitational pressure smashes the electrons into the protons, forcing them to combine and become neutrons. The entire star becomes a single, city-sized atomic nucleus, an ultra-dense soup of neutrons packed shoulder to shoulder, with virtually no empty space left at all. This is what leads to that staggering density. A single cubic centimeter of this neutronium, a sample no bigger than a dice, would have a mass of around 1 billion tons. To put that in terms we can almost grasp, a single teaspoon of this material would have a mass equivalent to every single human being on Earth combined, and then multiplied by 100. Or, to use another comparison, it would weigh about as much as a mountain like Mount Everest, all compressed into a volume you could hold in your palm. The physics of such an object is as strange as its density. The surface of a neutron star is thought to be a solid crust of atomic nuclei locked in a crystalline lattice, but with a density millions of times greater than steel. Beneath this crust, you'd find an ocean of a superfluid, a frictionless liquid that can flow without any viscosity, and a core where the density becomes so extreme that we can only speculate about its nature. Physicists theorize that the neutrons themselves might break down into a soup of their constituent particles, quarks, creating a state of matter not found anywhere else in the universe. The gravitational field on the surface is equally mind-bending. It is about 200 billion times stronger than Earth's gravity. If you were to somehow drop a marshmallow from a height of just 1 meter above a neutron star's surface, it would hit with the energy of 1,000 hydrogen bombs because it would be accelerated to a significant fraction of the speed of light. This incredible density also gives neutron stars other extraordinary properties. They spin at incredible rates, some completing hundreds of rotations every single second. As they spin, they can emit beams of radiation from their magnetic poles. If one of these beams happens to sweep across Earth, we detect it as a regular pulse, leading us to call them pulsars. These cosmic lighthouses are so precise in their timing that they rival atomic clocks. The very existence of neutron stars stretches our understanding of material substance to the breaking point. They are a form of matter that is fundamentally alien to our everyday experience, demonstrating that under the most extreme conditions, the universe can forge materials with properties that defy all intuition. They are a testament to the fact that the same laws of physics that govern a falling apple can, under the right circumstances, create a teaspoon of stuff that weighs more than all of humanity. But if our entire universe can be encoded on a two-dimensional surface, what does that say about the very nature of reality we touch and see? This brings us to one of the most profound and mind-altering concepts in all of theoretical physics, the possibility that our universe is a hologram. Before you dismiss this as science fiction, understand that this isn't about a shimmering light show or a computer simulation. The holographic principle is a serious, albeit deeply theoretical, idea emerging from the study of black holes and string theory, and it suggests that all the information that makes up our three-dimensional reality, you, me, the stars, everything, might actually be encoded on a distant two-dimensional surface like a cosmic DVD, and what we experience is merely a projection from that boundary. The story of this incredible idea begins not with holograms but with a puzzle about black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, which is a measure of its hidden information or disorder, is proportional not to its volume, but to the surface area of its event horizon. This was a radical departure from everyday experience. For any normal object like a book or a box of gas, the amount of information it can contain is related to its volume. A bigger box can hold more stuff and thus more information. But for a black hole, the maximum amount of information it can possibly hold is determined by the two-dimensional area surrounding it, not the three-dimensional space inside it. It was as if all the information about everything that ever fell into the black hole was somehow painted or encoded onto its spherical surface. Later, Leonard Susskind and Gerard T. Hooft took this concept and ran with it, proposing that this wasn't just a weird property of black holes, but perhaps a fundamental principle of the universe. The holographic principle boldly states that the description of a volume of space can, in theory, be encoded on a lower dimensional boundary to that region. To grasp this, think of an ordinary security hologram on your credit card. The hologram is a flat, two-dimensional piece of plastic, but when light shines on it, it projects a fully three-dimensional image that you can look around. The information for the entire 3D image is stored on the 2D surface. The holographic principle suggests our universe might work in a similar, though far more fundamental, way. The entire three-dimensional space we live in, plus the dimension of time, could be a projection from information stored on a vast, remote, two-dimensional surface at the edge of our observable cosmos. In this view, every particle, every force, every ripple of energy that we perceive in our 3D world is actually just a manifestation of incredibly complex data processing happening on this distant 2D screen. You are not reading this script inside a three-dimensional volume. You are, in a sense, a holographic projection. The implications of this are staggering. It would mean that our perception of a third spatial dimension is a kind of grand illusion, an emergent property that isn't fundamentally real. The true, fundamental workings of the universe would be happening on that two-dimensional surface in a realm where concepts like volume and inside have no meaning. This idea provides a potential solution to another thorny problem in physics, the black hole information paradox. If information cannot be destroyed, what happens to all the information about an object when it falls into a black hole that eventually evaporates via Hawking radiation? The holographic principle offers an elegant answer. The information isn't lost inside the black hole. It never actually falls in. Instead, it is smeared and encoded onto the event horizon as the object crosses it, and is then slowly released back into the universe as the black hole evaporates. While the mathematics behind this principle is incredibly complex and rooted in string theory, the core idea forces a profound philosophical shift. It blurs the line between science and philosophy, challenging our most basic assumptions about what is real. Are the solid objects around us truly solid, or are they just the most convenient way for our brains to interpret a vast amount of data flowing from the edge of space? The universe, in this view, becomes a cosmic mirage, a breathtakingly detailed and consistent illusion generated from a reality that is fundamentally simpler, flatter, and stranger than we could have ever imagined. And just as the cosmos has a baseline temperature, a faint warmth from its birth, it also possesses an ultimate, fundamental chill, a temperature floor beyond which it is impossible to go. We are talking about the coldest possible temperature in the universe, a profound boundary known as absolute zero. This isn't just a number on a thermometer. It's a fundamental limit imposed by the laws of physics themselves, sitting at negative 273.15 degrees Celsius or zero on the Kelvin scale. At this theoretical point, something truly profound is supposed to happen. All molecular motion would cease entirely. The frantic, jiggling dance of atoms and molecules that we experience as heat would come to a complete and utter standstill. Think of a bustling crowd in a town square. As you lower the temperature, the crowd's movement slows from a run to a walk to a gentle shuffle. Absolute zero represents the point where every single person in that square freezes in place, not a single muscle twitching. All the thermal energy has been sucked out, leaving the particles in a state of perfect, motionless rest. Now, in practice, reaching this perfect state of 0 Kelvin is physically impossible according to the third law of thermodynamics. You can think of it like trying to slow down a car by an infinitely small amount each second. You can get closer and closer, but you can never truly reach a complete stop in a finite number of steps. The energy required to remove that last tiny whisper of heat becomes infinite. Yet, the pursuit of this ultimate cold has led scientists to achieve temperatures within a few billionths of a degree above absolute zero. To get this cold, researchers use incredibly sophisticated techniques, most notably laser cooling and evaporative cooling. In laser cooling, atoms are bombarded with lasers from all directions, tuned to a frequency that essentially acts like optical molasses. As the atoms move against the laser light, they lose momentum and slow down, which corresponds to a dramatic drop in temperature. This gets them very cold, but to reach the ultra-cold regime, scientists then use evaporative cooling. Imagine the hottest, most energetic atoms in a magnetic trap as the fastest swimmers in a pool. If you could carefully skim off just these top athletes as they jump out, the average energy, and thus the temperature of the remaining atoms plummets. This is how we create a state of matter that simply cannot exist anywhere else in the natural universe, a Bose-Einstein condensate. When a cloud of certain atoms is cooled to within a whisper of absolute zero, a strange quantum phase transition occurs. The individual atoms, which normally behave as distinct particles, lose their identities. Their matter waves, a fuzzy cloud of probability that defines their position, begin to overlap and coalesce. They all fall into the same quantum ground state, essentially behaving as a single, giant superatom. This condensate doesn't act like a solid, liquid, or gas. It's a new form of matter where quantum effects, normally only visible at the tiny atomic scale, become apparent on a macroscopic level. You can see quantum weirdness with your own eyes. In this state, if you were to shine a laser through the condensate, it would slow to a literal crawl, potentially being slowed down to bicycle speeds. The condensate can flow without any friction or viscosity, a property known as superfluidity. If you were to stir a cup of this superfluid, it would theoretically swirl forever. Perhaps the most bizarre demonstration is that a superfluid can defy gravity, creeping up the sides of its container and dripping out from the bottom in a seemingly impossible leak. The pursuit of absolute zero has opened up an entirely new frontier for physics. In this ultra-cold realm, we can simulate the conditions of neutron stars, study the fundamentals of superconductivity, and probe the very nature of quantum mechanics in a controlled environment. It's a place where the familiar rules of our warm, busy world are suspended, and the universe reveals a more orderly, wave-like, and deeply interconnected reality that is always there, just hidden beneath the veil of thermal energy. This ultimate chill is not about creating a dead, sterile state. It's about unlocking a new window into the quantum heart of reality. This brings us to our final and perhaps most poignant, surprising truth. We are living in a privileged era, a cosmic golden age of observation that is fleeting. The very same dark energy that is accelerating the expansion of the universe is in fact setting a cosmic expiration date on our ability to see the greater cosmos, making this moment in time the best it will ever be for understanding the universe on the largest scales. Think of it this way: every galaxy beyond our immediate local neighborhood is like a ship sailing away from us on the expanding fabric of space. Right now, their engines are set to a gentle cruise, but dark energy is systematically pressing down on the accelerator. With each passing moment, these galaxies are not only moving farther away, but they are also beginning to recede at faster and faster speeds. There will come a time, billions of years from now, when the space between our galactic groups is stretching so rapidly that the light from those distant galaxies simply cannot overcome the ever-widening gap. They will not vanish in a flash. Instead, they will gradually fade, their light stretched to longer and longer wavelengths, redshifting first into the infrared, then into radio waves, and finally into undetectability. Their images will dim like a lighthouse beacon being swallowed by an impenetrable fog, until they cross a cosmological event horizon and disappear from our view entirely. Future astronomers born in galaxies like our Milky Way trillions of years from now will look out into a profoundly different and much emptier sky. The evidence for the Big Bang, the cosmic microwave background radiation, will have been stretched to such long wavelengths that it will be undetectable. The countless galaxies we see today in deep field images from the Hubble and James Webb Space Telescopes, each a tiny smudge containing billions of stars, will be gone. The universe will appear to contain only their own galaxy and a handful of nearby, gravitationally bound companions, all adrift in an immense, black and seemingly static void. They will have no clues that a vast, populated and evolving cosmos ever existed beyond their own island. They might logically conclude that their galaxy is the entire universe, with no evidence of a beginning or a larger structure. We, on the other hand, exist at a special crossroads. The universe is old enough to have produced the heavy elements necessary for planets and life, yet young enough that the cosmic lights are still on all around us. We can still see the afterglow of creation. We can map the large-scale structure of the cosmos. We can trace the history of galaxies from their infancy to the present day. We are like the first people to arrive at a magnificent, star-filled festival, able to see all the attendees and witness the grand spectacle. Our distant descendants will be like those who arrive after most guests have departed, left to wonder what the excitement was all about, with only faint echoes and empty spaces as clues. This isn't just a theoretical fate, it's a process that is already underway. The light from the most distant galaxies we can detect has been traveling for over 13 billion years to reach us, a testament to how much of the universe is still within our view. But the window is slowly closing. This profound realization adds a deep layer of meaning to our scientific quest. Every observation we make, every deep field image we capture, is not just data, it is an act of cosmic preservation. We are compiling the photo album of a universe in its vibrant youth, creating a record for all of time, because the universe itself is in the process of erasing the evidence. We are the first and perhaps only generation of astronomers in the entire cosmic timeline who will be able to perceive the full grandeur and scale of the cosmos. It is a tremendous responsibility and an incredible privilege, a brief, shining moment in the dark to comprehend the magnificent story of everything. And so, our journey through these 30 astonishing revelations comes to a close, but the view it leaves us with is anything but final. From the humbling reality that our familiar world is but a tiny fraction of a cosmos ruled by invisible dark matter and dark energy, to the quantum foam where nothingness seethes with existence, we've seen how reality constantly defies our expectations. We've witnessed time as a personal experience, explored the centerless expansion of the universe, and discovered that our very atoms are stardust, forged in the hearts of long-dead stars. We've contemplated the possibility of a multiverse, the slow evaporation of black holes, and the spooky connection of entangled particles. We've journeyed from the bizarre retrocausality of the quantum realm to the majestic, impending collision of our galaxy with Andromeda, and from the ultimate chill of absolute zero to the mind-bending possibility that our 3D reality is a holographic projection. Each of these truths on its own is a staggering shift in perspective, but taken together they weave a single, overwhelming narrative. The universe is not just a collection of objects in space obeying simple, predictable rules. It is a dynamic, evolving, and deeply interconnected system, brimming with mysteries that challenge the very foundations of logic and perception. It is a place where planets can float, where days can last longer than years, and where the number of trees on our small world can rival the stars in our galaxy. It is a reality that is far stranger, far more beautiful, and infinitely more wonderful than the static, orderly cosmos we often picture in our minds. This new understanding is not meant to make us feel small, but to make us feel connected. We are not passive observers on a tiny rock. We are active participants in this grand cosmic story. The laws that allow a star to shine are the same laws that allow our hearts to beat. The same curiosity that drives us to look up at the stars is a product of the very universe seeking to understand itself. Your act of watching this video, of pondering these ideas, is a testament to that beautiful, self-reflective loop. So, the next time you find yourself under a clear night sky, I encourage you to do more than just glance upward. Really look, see past the familiar patterns of the constellations and perceive the depth behind them. See the vast emptiness that is actually a quantum sea of potential. See the distant galaxies that are racing away into a future of isolation. See the faint possibility of rogue worlds and hidden planets. See the echo of the Big Bang in the very cold of space and the history of stellar explosions written in your own hand. Let that sense of awe wash over you, not as a fleeting feeling, but as a new way of seeing your place in this incredible, unfolding story. The exploration doesn't end here. This conversation is just beginning. I want to hear from you. Which of these 30 truths surprised you the most? Which one fundamentally shifted your view of reality? Share your thoughts in the comments below. Let's create a community of cosmic wonder, learning from each other's perspectives. If this journey has sparked your curiosity, if it's left you with more questions than answers, then you're in the right place. This channel is dedicated to diving deep into the mysteries of space, time, and existence itself. To make sure you don't miss our next adventure into the unknown, be sure to subscribe and hit the notification bell. There are countless more wonders waiting to be uncovered, and together we can continue to explore the greatest story ever told.